everyone studying for the midterm going? Okay. So a couple of announcements. I know on the website it says single-sided, but as I mentioned in the announcement, you can use a double-sided aid sheet. Again, use the aid sheet to study. I think you're on a 50-minute test time, so really it's going to be a hustle to finish in time. So yeah, you have a question. Double-sided. Yeah, so I just wanted to clarify that. I know it says single on the website, but on the announcement I had said double-sided, so I'm going to stick with that. Yep. You can do whatever you want with it. Just don't staple two pieces of paper together because you won't be able to figure out how to print double-sided in time. That's the only thing that I ask. As long as you just carry a single sheet, it's fine. So homework 3 is out. It's going to be due a little after reading week, and we'll release the project a little before reading week, so you'll have an overlap. It's really up to you if you want to take a look at it. If you get done with homework 2, submit it early and get started on your projects, and that's totally fine. Okay, and so in terms of midterms, the only strategy that I have as advice, and I gave this to folks who came by in office hours, is to finish the questions that you know how to answer very quickly, and then move on to the harder ones. And so remember, like the test is, you're going to show up at EX 200, it'll take you 5 minutes to sit down, and then you're going to be starting right away. So just use that as a strategy to finish all the questions that you're comfortable with and you're confident of the answers on before you move on. So today's lecture is not going to be covered on the midterm, so you can sort of relax and just absorb the material and think of it as a break from the midterm studying. But what we're going to do is try and give you an introduction to probabilistic modeling. And, you know, we've sort of circled around these issues of how do we come up with these loss functions and how do we think about why is the mean squared error a good loss function and why is cross entropy a good loss function. And in many ways we motivated it from an optimization perspective. We said that they were good loss function because they satisfied sensible properties. But you could always ask, is there a more foundational reason to those choices? And what I'm going to tell you about today perhaps starts to give you an intuition for why that might be. And this is going to be things that we build on for the rest of the second semester of this class. So we'll start off with probabilistic modeling of data, and then we'll introduce a completely new kind of classifier this lecture. And that's going to be called a generative classifier. And we're going to introduce it as an introduction into unsupervised learning in general. But this class of classifiers does prediction using a fundamentally different mechanism than everything that we've learned before. So up until now, we've adopted this sort of modular perspective in machine learning. We've started out with some kind of a model. We've said for this model, we're going to devise this number, this loss function that tells us how different are the model's predictions from the thing that we care about predicting. And then for that loss function, we've defined an optimizer. We've said that we want to minimize that loss function with respect to the parameters of the model using gradient descent, stochastic gradient descent, batch gradient descent, and these were different choices of optimization strategies that we developed. Finally, we wanted to prevent overfitting, so we devised strategies to minimize the norms of the weights as one form of regularization. And so what I want to do today is really try to convince you that all of these things can be seen through a unified lens. And that unified lens is going to be a probabilistic interpretation of both the model and the loss. And in this lecture, we'll introduce the concept of maximum likelihood estimation. But before we go through that, what we're going to do is start with really just a simple example of data and prediction. And that example is that of you as a practitioner tossing a coin about 100 times. So if you flip a coin 100 times and you record the outcomes, x1 to x100 here in this set. And each element of this set is going to be a binary number where 0 indicates tails and 1 indicates a heads. So the setup is simple. You're going to toss the coin 100 times, just record whatever you saw. And you're going to use this as your data, and your goal is to come up with a model that is going to be good at predicting the outcome of the next coin flip. So that's your goal in the context of what we're going to talk about next. And so the question, if we model that mathematically, is what is the probability that this coin that we have, that so far has about maybe 55 heads and 45 tails, what's the probability that it's going to come up heads again? That's a good way to think about a predictive model of what's going to happen next when you flip this coin, which is to say if you had that probability, that number, you could with some degree of confidence predict what's going to happen next with this coin. So any questions about the setup so far? Okay, so we just have this coin, we flipped it, we got some data, and now we want to come up with this model. So in the past, we came up with different choices of models that characterize the relationship between inputs and outputs. What I want to ask you now is what kind of probability distribution might we be able to use as a reasonable way to model coin flips? Yeah. So the one answer was a uniform distribution, and that's not quite right, because remember, when we're flipping a coin, we only see one of two things. We see either a 0 or a 1. And a draw from a uniform distribution can be any number between 0 and 1. So you can get a 0.7 as a draw from a uniform distribution, but that's not a valid number for a coin to be flipped as. So what distribution would you use? Yeah. Could you say that louder? Bernoulli distribution? That's right. So you would use a Bernoulli distribution to model a coin flip. So how many of you are familiar with this distribution? Okay, so some of you have seen this before, but a Bernoulli distribution is a way to model binary outcomes. And so if you had a coin that you wanted to flip, you could use this Bernoulli distribution in order to model the outcome of it. So one Bernoulli distribution has a parameter, which is to say that that parameter controls the likelihood of seeing a 0 or a 1. And that parameter is a number that lies between 0 and 1. So this parameter is a knob for the Bernoulli distribution, and by turning that knob, you can control the number of times you see a 0 when you draw from this Bernoulli distribution, or a 1 when you draw from this Bernoulli distribution. So we're going to call this parameter theta, and that's a number between 0 and 1. And the way that the model captures the probabilities of different outcomes under the, for a Bernoulli random variable is it says that the probability of drawing a 1 under a Bernoulli random variable is equal to theta. So the parameter theta is nothing more than the probability of seeing a 1 being drawn when you draw from this Bernoulli random variable. So this knob is just saying how likely is a 1 to show up. And the probability of x being 0, x is our random variable that we're modeling, is going to be 1 minus theta. So it's 1 minus the probability of seeing a 1, which is the probability of seeing a 0 for this Bernoulli random variable. So remember, it's important to distinguish what the parameters of a distribution are from the realizations of that of random variables that are drawn from that distribution. So realizations of draws from a Bernoulli random variable are binary, so they're 0s and 1s. But the parameter of a Bernoulli random variable is a number that lies in the unit interval. It's a number that can be 0.75, 0.69, whatever you want. Any questions about the setup of this problem so far? Okay. So one way to succinctly write down the probability of drawing any assignment to this Bernoulli random variable under this parameter theta, so the probability of any assignment x under this Bernoulli random variable is given to us by this equation. And this equation is nothing more than a compact representation of the two lines above it. Because what it's saying is that when x is equal to 1, the probability of seeing a 1 under this Bernoulli random variable is just going to be given to us by theta. So when x is equal to 1, this term is going to be ignored, and it's just going to be the first term that controls the probability. And when x is equal to 0, this first term gets ignored, and it's going to be the second term that controls the probability. So this is just a compact way of writing down these two statements about how the probabilities of assignments for a Bernoulli random variable behave. Now that we're at this point where we have this Bernoulli random variables, we can start thinking about the data that we collected from this coin flip experiment. So we took this coin, we flipped it 100 times, we got a set of data. Each time we flipped this coin, we did not look back or manipulate the coin in any way as a consequence of what we saw in the past. And so each of these draws from this hypothetical model that we have posed are said to be independent and identically distributed. They're independent because there is no relationship for the current draw with respect to anything that's been drawn before. They're identically distributed because we're making the assumption that they're all drawn from this same Bernoulli random variable. So this assumption IID means that each of the different instances, x1, x2, x3, all the way to xn, are drawn from the same distribution, in this case this Bernoulli model that we're posing, and they're going to be identically distributed. So remember, we can pose what the probability of a single event x is, and equivalently we can pose what the probability of an entire outcome is. So the joint probability distribution of observing n events from a random variable, when the events are identically distributed and independent, so when the events are IID, can be written as the product of the probabilities of those independent events. So the probability of x1 to xn, given this Bernoulli random variable with parameter theta, can be written as a product of I is equal to 1 to n of the probability of xi given theta, and each of the probabilities of xi given theta can be compactly written with this equation that I'm highlighting here. Okay, so what we did in this page is essentially use this model that we're pretending generated the data to write down what the probability distribution is over the events that we observed in practice. And now what we're going to do is represent this as a likelihood function. So we're going to say that the joint probability distribution of observing the data as a function of our parameters theta is going to be called the likelihood, because it's a function that tells us how likely the observed samples are under the model that we have. And the likelihood function for this data under this model is given to us by the product of P of xi given theta. It's just the joint probability of observing all of the events, which is the likelihood of the data, and it's the product that we had in the previous slide. So we usually don't work with the likelihood function itself. We're going to work with the log likelihood function. And so the log likelihood function is just the log of both the left-hand side and the right-hand side. And when you take a log of product of things, it becomes a summation. And when you take the log of a number that is exponentiated, the exponent comes down and becomes a multiplier on the log of the number. And so when you move the log inside this product of events, it first turns into a summation, and the log operator distributes the exponents as coefficients. So why do we work with log likelihoods rather than likelihoods themselves? Yep. Right. So what happens when you think about, so the answer was the products can be difficult to work with. And one reason why they're difficult to work with is essentially, think about what happens when you multiply 0.05 with 0.05. You get, 25 times 1e minus 4. And when you start multiplying these small numbers that are all less than 1 together, you quickly experience numerical underflow in any practical implementation of the product of very, very small probabilities. And so from a practical perspective, you would really want to avoid multiplying small numbers that are less than 1 together, because your computer has only a certain number of bytes in order to be able to represent numbers. And so if your number is very, very, very tiny, your computer is going to experience what's called numerical underflow. And the other reason, as was pointed out, was that the log operator is monotonic. So things that have a high likelihood are also, events that have a high likelihood are also going to have a high log likelihood. And similarly, events that have a low likelihood are also going to have a low log likelihood. And so the precision of representation of probabilities, as well as the convenience of working with the logs in terms of distributing products into summations, is why we work with the log of this function. And now we're sort of ready to apply some of the intuition that we've developed in the first half of this class to this problem now. We can ask, we have some data, we posited this Bernoulli random variable as a model for the data, but thus far, we don't yet know how to set the parameter theta. So how do you set it? Well, the principle of maximum likelihood estimation says that you should pick the value of theta that is going to maximize the log likelihood of the observed samples under the model. So just like in supervised learning, we tried to learn our parameters so that the prediction matched the target. We're trying to learn the parameters of this model, this Bernoulli random variable, so that the log likelihood of the data under the model is as high as possible. So good values of theta should assign high probabilities to the observed data. And we're going to use the maximum likelihood criteria that's going to maximize the following log likelihood. So we're going to solve the following optimization problem in order to get theta hat ml, and this is the maximum likelihood estimator for the Bernoulli random variable that we have. So I'll pause here to see if anyone has any questions about the principle of maximum likelihood estimation. Yeah. Yeah. So theta, remember, is the parameter of this Bernoulli distribution. So the question that we started out with was that we had a bunch of coin flips, and we wanted a model to predict what the next coin flip was going to be. To have a model to predict what the next coin flip was going to be, we needed a distribution to model coin flips. So we picked the Bernoulli distribution, and the Bernoulli distribution has this parameter theta. And so we've observed some data now, and we want to know how do we set the value of this parameter theta so that it becomes a good model for us to use in the future to predict what future coin flips are going to look like. And the principle of maximum likelihood estimation says you should choose your parameter theta for this model based on the value of theta that maximizes the log likelihood of what you've actually observed. Because if it's a good model for the data that you've observed that you want to continue using to predict things in the future, then it should at least explain the data that you've observed well. And for a model to explain the data, it means it has high probability mass over the observed samples. And that's effectively what the log likelihood is doing. Okay. So how do we solve this optimization problem? What we're going to do is use the standard trick of identifying a critical point of this objective function. And that's going to be done by setting the derivatives to 0. So we're going to take the derivatives of the log likelihood function, and that's going to be the d by d theta of the summation that we had in the previous slide. We can move the derivative operator inside the summation. And remember, it's only these two terms that depend on theta. So what we end up getting is a summation over xi over theta minus a summation over 1 minus xi over 1 minus theta. Now it's important to note that the summation over xi is going to do nothing other than count the number of heads that you have, and the summation over 1 minus xi is going to count the number of tails in your data set, which is why we can replace them by nh over theta and nt over 1 minus theta respectively. And so this is what the derivative of the log likelihood of a Bernoulli random variable is under n different trials of flipping flipping coins. And now we're going to set this to 0, and you're going to get the maximum likelihood estimate, which is what's called theta hat ml. And the form of the maximum likelihood estimate is very simple. It says look at the number of heads in your data set and divide that by the total number of times, or total number of data points, which is the number of heads plus tails. So it's saying nothing more than that the maximum likelihood estimate for your parameter theta for this coin flip is going to be the fraction of times that you saw heads. So if you flip this coin 100 times and saw 70 heads, then theta ml is going to be 0.7. And that's telling you that if you're going to use this number as a model to predict what's happening in the future, there's a 70% chance you'll see a heads in the next coin flip. So just as a mechanical exercise, I've derived the gradient and just done the algebra for setting the gradient to 0. So I'll take you through that really quickly, but this should be easy material for you as you're studying for the midterm, because we've done it a few times in the past. So this is where we started out with, and we're going to set this to 0. So we're going to move this over to the right-hand side to get this equation. Next, we're going to move this over to the right-hand side and move this over to the denominator to get this equation. Then we're going to simplify the left-hand side as 1 divided by theta minus 1. We're going to move this minus 1 to the right-hand side to get this equation. And then we're going to end up moving, we're going to end up trying to create a fraction on the right-hand side, which gives us nh over nt plus nh. And then we're going to reciprocate both sides to give us the answer that we get in the previous slide. So this is just taking you through the algebra of what you need in order to derive the maximum likelihood estimator by setting the derivative to be 0. So any questions about what we've done so far? We started out with some data. We wanted a model to predict what the next value from this coin would look like, heads or tails. So we posited this probability distribution, this Bernoulli random variable, that might help us develop a model. Then we needed to know what parameter should I use for the Bernoulli random variable itself. In order to do that, we use the principle of maximum likelihood estimation to figure out what the right setting for the parameter theta is. Once we had that parameter configuration for theta, we were done. Like, we can now use this as a model to predict what might happen in the future with this coin. Yeah?
So there's no parameter learned in this model?
There is a parameter learned. The value of theta, this is the parameter that you're learning, and that's using numbers that you've obtained from the data set that you have. Because this is the number of heads you've seen so far, and this is the total number of flips. Okay. And so in maximum likelihood estimation, we define this model that assigns a probability or has a probability density at any given data that is observed. And we maximize the likelihood or minimize the negative log likelihood of that model under this data set. And that's the principle that we adopt. And so that gives us the technical machinery now to start thinking about a new kind of classifier. And in order to know why it's new, we need to distinguish between classifiers that we've learned before and the one that we're going to learn about today. So in machine learning, so far we've seen inputs and outputs. And all we've done is come up with different kinds of functions, whether it's decision trees or neural networks or linear models, that can take these inputs and predict outputs. And so let's start from a really, really simple example of spam classification. So let's say you're running Google, and one predictive problem that you have is to predict whether or not an email is spam. So this is an email that represents postponing some kind of a meeting, and we can see that this does not represent spam, or to most of us this would not represent spam. This is another email that talks about mining some bitcoins, but this intuitively strikes us as looking a bit spammy. So if you were responsible for solving this problem, what might you do in order to solve this using the tools you already know? Like, what's the first step you would do to get features in order to solve this problem if you were working at Google? Yeah?
Identify keywords that are in non-spam versus spam.
Yeah, so the inputs to your model are essentially these emails, and emails comprise words and words are interesting features that might be relevant for the prediction of the probability that an email contains spam or not. And so what we're going to do, and what we've done in the past, would be to extract the words from these emails and apply a discriminative classifier. So we might apply logistic regression or neural networks with a logistic output in order to predict the probability of spam from the set of words that we have. And when we did that, what we were doing is that we were modeling the probability density of y given x. And the reason we know that that's true is thinking back to some of the early work we did on bias variance decomposition when we talked about the best possible model matching the conditional expectation of the true labels given x. So every discriminative model that we've learned so far is attempting to model P of y given x as closely as it can. Generative classifiers don't do what the models we've learned about do. Instead, what they try to do is something very different. They try to build a model for what data for a class actually looks like. They try to figure out a model for the joint distribution of both the emails as well as the class label for whether or not the email contains spam. And once they have this joint distribution, they can easily compute the outcome label. So remember, when learning classifiers, we have access to labeled data sets. And what we're going to do is to learn the probability of a feature given a label. So we're going to learn a distribution over all the words that occur in a spam email and a distribution over all the words that occur in a non-spam email. And then we're also going to have access to the probability that any given email is spam or not spam. And once we have these numbers, we can use the idea of Bayes' rule to do prediction. So to take a step back, discriminative classifiers like the ones we've learned before and the ones you'll be tested on estimate parameters of decision boundaries or class separators directly from labeled examples. So you're taking labeled examples directly and you're attempting to model this P of t given x, the probability of a target given an input. And you do this by learning functional mappings from inputs to classes. So these functional mappings could be decision trees, so these axis-aligned splits. These functional mappings could be linear functions in the form of logistic regression, or they could be nonlinear functions in the form of neural networks. But the basic problem discriminative models approach is how do you separate the classes given some input data? In contrast, generative models model the distribution of inputs. They try to understand what kinds of features are more likely in one class versus another. And they apply Bayes' rule to derive the probability of t given x, the class label given a new test point x. And so they try to solve this problem of what does a class look like? Because if I know what every possible instantiation of a class looks like, then I can use that knowledge to infer what the class label for a new class is. So the key difference between the two to keep in mind is whether or not there is a distributional assumption over the inputs. What does it mean to have a distributional assumption over inputs? It means that you are going to pose a probability distribution that characterizes how the input features behave. And we'll learn how to do that in the context of some of the generative classifiers we'll talk about today. So before we jump into naive Bayes, now is probably a good time to take a quick break. So let's reconvene at 1:45 to continue. If you have questions about anything I've talked about or the midterm, just come by. Like we covered what a combination operation is, we covered what a one-way combination does, and what a three combination does. So mathematical operation. From a combination operation, we effectively know like properties of a combination operation. Do we have non-linearities? Do we stack them? Things like that. That's about the extent. So like we're not going to ask you coding questions. We haven't covered much of that. All right, so let's get started. So in the first part, we talked about the idea of modeling the probability of observing different kinds of coin flips. And then we talked about introducing generative classifiers. And these classifiers effectively operate by looking at the probability of features given a class and using that in conjunction with Bayes' rule to invert and infer what the class label is. So let's think about that in the context of a very concrete model, and this is the simplest kind of generative classifier you can have, and it's called the naive Bayes model. So our goal is going to be to classify email into spam versus not spam. So C is equal to 1 is spam, C is equal to 0 is not spam. And what we have are binary features, where each element, so we have a d-dimensional input feature vector, and each element of that d-dimensional feature vector is a binary number. So each xi is binary. And what it says is whether each of the d words appear in the email. So it's a one-hot feature encoding for the email itself. So, sorry, I shouldn't say one-hot, because one-hot implies there's only one in that vector. This is a binary representation of that email. So as an example, if you got this email, you are one of very few who have been selecting as a winner if it's a free $1,000 gift card. Then what you're going to do is you're going to take your entire vocabulary, which is the set of all the words you see in the training distribution, and you're going to create a feature vector that is of dimension d. And associated with each location in this feature vector is a word. So you can sort your vocabulary alphabetically, and you might have words like card, winners, winter. And essentially, this feature vector is going to have a bunch of ones and zeros. If the word occurs in the email, you're going to put a 1 in the corresponding location for that feature in that vector. So if card appears in the email, which it does in this example, you're going to put a 1 in that location. Winners appears, or winner appears, so you're going to put a 1 in that location. Winter does not appear, so you'll have a 0 in that location. And so that's how you're going to take this data, which is a sentence, and convert it into a binary feature vector. So as before, in machine learning, we're going to have these binary features as our inputs, and in conjunction, we're going to have these class labels. So for each feature vector, we're going to have a class label that's going to tell us whether or not that feature vector is a 1 or a 0. Any questions about the setup? Yep.
What if like your email is just full of typos and it's like very obviously a scam?
Right. So what you would do in that particular case is you would have a vocabulary set such that even mistyped words would have their own location in this feature vector. Because ultimately, the only thing you can do when you're creating this feature vector is to have a vocabulary that captures the different variations of words that you observe. And so what would end up happening, or at least if you were to train a discriminative model with that feature vector, you should expect that there's a high weight associated with misspelled words. That's going to tell you that it's highly likely to be spam. But we'll see what happens in the context of a generative classifier. Yes?
So it could be very, very large?
It could be very, very large. Okay, so now we have a feature that's d-dimensional, and we want to compute the class probabilities using Bayes' rule. So how many of you remember what Bayes' rule is? Okay, so that's most of you, and you should have covered it in your probability classes, but I'll recap it here. Bayes' rule says that if I want the probability of C given X, then I can first estimate the probability of X given C, multiply that with the probability of C, and divide that by the probability of X. So the easy way that I use to actually remember this is if I have any A given B, and I want to estimate that probability, that conditional probability, I just need to be able to estimate B given A times A times B, and the probabilities of each of these events. So flip these orders, and then this goes in the numerator, and this goes in the denominator. So that's Bayes' rule. So it says if I want the probability of a class given any given feature vector, then I need to estimate the probability of the feature vector under that class, and I need the probability of the class. And then I'm going to divide that by the probability of x. So this left-hand side has a specific name for it, and it's going to be called the posterior distribution. And the reason it's called the posterior distribution is because it is estimated after observing some data. And in this particular case, you are estimating the posterior distribution of the class after looking at what is in the set of data X. So the posterior distribution for class C is going to be the prior distribution of the features given the class multiplied by the prior distribution for the class. So let me be very concrete about what I mean here. I can estimate probability of C is equal to 1 given X as the probability of X for any test point X given C is equal to 1 times the probability of C is equal to 1 divided by the probability of X. And similarly, I can also estimate the probability of C is equal to 0 given X as the probability of X given 0, C is equal to 0 times the probability that C is equal to 0 divided by the probability of X. Now what you'll note here is that in the binary case, I don't actually care about what's in the denominator on the right-hand side, because that denominator is the same across both of these terms. So the only thing I need to use is the numerator. And by looking at which of the numerators is bigger, I can make a decision about whether or not the point is in the spam class or in the non-spam class. So that's what it means when it says to compute P of C given X. We really just need P of X given C and P of C. Any questions about this? So I haven't told you how to actually solve this problem. I've just told you that if I had access to these numbers, I could use Bayes' rule to solve this problem. So what we're going to do next is think about where these numbers actually come from. Okay, so to figure out where these numbers come from, we need to come up with a representation for probability distributions over binary variables. How many variables do we have? Well, we have one variable for which class it is, and we have D variables for one for each of the features. So we have D plus 1 binary variables. The joint probability distribution over D plus 1 binary variables requires 2 raised to D plus 1 minus 1 numbers. Is that clear as to why it's 2 raised to D plus 1 minus 1? So remember, like whenever you see things like this, just substitute it in a real number to get an intuition for why that number takes that value. So let's say we only had exactly one feature, then we would have 2 numbers that we would need to represent the joint probabilities of. If we have 2 numbers we want to represent the joint probabilities of, we need to consider all the possible configurations you could have. And that's 4 configurations. So you need numbers A, B, and C for the first 3, and you know that the last one, because all probabilities sum to 1, can be represented via this number. So you need 2 raised to 2 minus 1, which is equal to 3 numbers, in the case where D is equal to 1. And that generalizes as 2 to the D plus 1 minus 1 numbers in the D-dimensional case. And that's a lot of numbers. So as one of your colleagues pointed out, D can be very big because it's the vocabulary of all the words that could occur in emails. So if you have 10,000 words, it's 2 to the 10,000 plus 1 minus 1. And that's a lot of numbers to put into storage. And even if you could store it, you'd never really want to do that. And so the question we can ask is whether we can impose some structure on the distribution so that representation of the joint probability distribution is compact, which means it can be done from using a small number of numbers, and that it allows for efficient learning and inference. and we'll know what that means in a bit. Any questions about about this slide, about the complexity of representing joint distributions over d+1 numbers? Yeah.
So when you said that we could have 10,000 as our number for D, because 10,000 words for dictionary,
Yeah.
how do we pick those specific words?
You would just pick the union of all the words you've observed so far. Okay. So to help us incorporate this structure, we're going to make an assumption. And this is the assumption that is embedded into the naive Bayes model, and it's called the naive Bayes independence assumption. The assumption that we're going to make is that each feature xi is conditionally independent given class label C. So do folks have questions on what the notion of conditional independence mean? If two variables are independent, it means that their probability distributions do not influence one another. So if you have variables A and B that are independent, then the probability of A comma B is equal to probability of A times the probability of B. If two variables are conditionally independent, it means when you know the value of what is in that conditioning set, then you can factorize the probability distributions of those two variables. So if you know that P of A comma B are conditionally independent given C, then the joint probability of P of A comma B given C factorizes as P of A given C and P of B given C. But that's just the mathematical notation for what conditional independence actually means. It's much more important that you get an intuitive understanding of what this is saying. It's saying that if I have the class label, that if I know that a given email contains spam, it means that the probability of observing any two words, any pair of words, or any triplet of words are all independent of one another. Which is to say, if I saw the word Bitcoin, that probability is independent from the probability of seeing the word mining in that same email, in that same spam email. How many of you think this is not a good assumption? That's right. Could someone tell me why? Yeah.
Some words typically have like dependence relation to others, or they're seen more frequently with certain others.
That's right. Emails have structure to them. Even spam emails have structure to them. And words co-occur with each other in ways that are very predictable. And so this assumption is in fact incorrect. But that's the very reason it's called the naive Bayes assumption, because it makes a very naive assumption about how the relationships among the words behave given the class label. But as you will see, despite the fact that it's a naive assumption, it's still a very useful one to make for us to make progress when we build this generative classifier. So we're going to decompose the joint distribution with this assumption as P of C comma x1 given xt as probability of the class label times probability of x1 given C dot 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 all the way to probability of xd given C. Why is this true? Well, the easiest way to prove this identity is to note that you're first going to use the chain rule over two sets of variables, this and this. And the chain rule tells you that you can decompose the joint distribution over those sets as P of C times P of x1 to xd given C. Next, you're going to use this conditional independence statement to simplify the second term here, to write that as x1 given C all the way to xd given C, because that's the mathematical definition of what conditional independence actually means. So that's how we get to factorize the joint distribution. Okay, so what have we done? How many numbers did we need to represent the thing on the left? that, what's that? The thing on the left, sorry. So if we did a naive estimation of it, we would need 2 to the d plus 1 minus 1 numbers. But because we've made this assumption, on the right-hand side, we can factorize it. And on the right-hand side, we need exactly 2d plus 1 numbers in order to represent the probability distribution over all of the features given the class label and the probability distribution over the class label. How do we get 2d plus 1? Well, we need 1 for the probability of the class, so this term. And remember, for each conditional probability, you need one number when c is equal to 1, and you need another number when c is equal to 0. And you have d such features, therefore you need 2d plus 1 numbers. And what are these numbers? Well, the first one is just the probability of the class label being spam. And the second and third number for each, the two numbers for each feature are the conditional probabilities of the features given the class. So each theta j c is going to be the probability of feature j occurring in class label c. So that's feature j occurring in a spam email or feature j occurring in a non-spam email. So who thinks this identity is true? I don't see a lot of hands, which is surprising, but it's basically telling you, but this identity should hold true in most spam emails, because what it's saying is that the probability, you should expect that there is a higher probability of seeing the word Bitcoin appearing in a spam email than in a non-spam email. So each of these features is interpreted as these conditional probability distributions. Any questions? Yeah.
Why is like the probability specifically representing like the spam? Because doesn't it like just looking at it, doesn't it just say the probability that like that this feature shows up? And then what does the class represent again?
Whether it's spam or not.
Okay. Okay.
So that's why you need two numbers. Because remember, this each feature is a binary number, right? Like it's a 0, 1. And you need one number to represent the probability of that binary feature being 1 when in a spam email, and you need another number to represent the probability of it being 1 in a non-spam email. Yes? Oh, you mean the fact that theta of like Bitcoin, comma spam is greater than theta of Bitcoin, comma not spam. Yeah. No, this is not false. This you should expect this to be true. Yeah. Okay. So we won't go through this figure in a lot of depth, but it's really important to note that these kinds of assumptions, like the ones made in the naive Bayes model, are found throughout machine learning. And Judea Pearl won the Turing Award for the development of what are called Bayesian networks. He formalized the idea that you could create compact factorized representations of complex, large joint distributions by incorporating conditional independence in them. And furthermore, he created this intuition that you can actually map those conditional independent statements graphically. And so this graph is the Bayesian network for the naive Bayes model. And The reason why this is so useful and interesting is that the arrows allow you to read out all of the conditional independence statements that exist in this model. In this particular model, the conditional independence statement that we know holds true is that P of xi given C is independent of P of xj given C for all I comma j. And the way that you would observe that in the context of this particular Bayesian graphical model is you would note that if you conditioned on C, you could treat that graphically as blocking the influence that any variable xi would have on any variable xj. So we won't go into a lot of detail in this class, but if you're interested in thinking of how these kinds of models can be built, scaled up, and learned, the class you should take moving forward is CSE 412 because it dives deep into what I call probabilistic graphical models, which are a really cool way to incorporate prior domain knowledge into these learning systems. And so we can form this graphical model, and as I mentioned, to specify this distribution, we need 2D plus 1 numbers, and this enables us to get around the computational complexity of representing that really big joint distribution that would need to be represented otherwise. So we're now sort of ready to go back to the question that we had posed before, which is, given a new test label, we can estimate Bayes' rule. So we can answer queries about which class a new test point is in, as long as we have a good model for P of x given C and P of C. So what we want to do right now is figure out how do we get that model in the first place? How do we get the parameters of those 2D plus 1 numbers that are going to be able to represent the probabilities of seeing these words and features together with spam and not spam? So exactly like we did in the example of flipping coins, we're going to write down the likelihood function of the data given the model parameters, or in this case, the log likelihood function. So what is our data? Our data in this case is going to be a set of feature vectors, each of which is d-dimensional, and associated with them are numbers. So we have n data points. Each of these is d dimensions. We're going to call this one x1 all the way to xn. And we're going to use the, this should be a superscript. So we're going to use superscripts to indicate the data point. So x superscript I is going to indicate the ith data point, and c superscript I is going to indicate the cth label. So this is data exactly like we've seen before in linear regression, logistic regression, and any of the supervised learning tasks. But what we've done here is create a generative model for the data, because we have a model of how the features behave given the class labels. And that's going to be those theta JCs, which is what's the probability of a given word given that the class is spam versus not spam. And we also have another number that's going to be the probability of an email being spam overall. So we need to find a way to estimate these parameters. And to estimate these parameters, we'll turn to the principle of maximum likelihood estimation. And remember, the principle of maximum likelihood estimation says that you should take your model's parameters and write down the log likelihood of the observed data using the model parameters. So you're going to write down this log likelihood function that's going to be a function of your model parameters that is going to tell you how likely the data is under the model. For this choice of model, we have the following parameters: pi and theta jc for all j comma c. So we have these 2D plus 1 parameters that we're going to use this capital vector theta to represent, and the log likelihood of this data set is going to be the summation of the log probabilities of each pair of ci and xi. So any questions up until here? Any questions about why we're doing this, why we got this equation, why is it a summation, and why is it a log. Okay, so if most of you are comfortable with the idea that in order to do parameter estimation via maximum likelihood estimation, we need to maximize the log likelihood of this data set, and we're assuming that the data set is drawn IID, and so that's why we get the summation over the log likelihood of individual points, then we need to find a way to simplify this equation. So the first step algebraically is going to be to write down, using the chain rule, the probability of xi given c times p of c as the factorization of the joint distribution. So that's the first step. Then from here to here, we're going to use the fact that each of the features are IID given the class label. So this is the naive Bayes assumption that enables us to write down that for each of the features, we can write it as a product of probabilities of the individual features given the class label. Next, we're going to move the logarithm inside this product of d plus 1 probabilities to write this down as a log probability over the class label plus a summation over the d features of the log probabilities of each feature given that class label. And finally, we're going to move this summation inside, and so we get the first term in this expression, which is a summation over the n data points of the log probability of each data point being spam, and a second summation where you have a summation over the d features, and inside each summation is a summation over the n data points, because we've exchanged the summation over n and d in this step. And each of these summations is telling us the log likelihood of observing feature xj under class Ci over the entire data set. And so let's first ask this question. So we have this log likelihood. This log likelihood is now a function over the parameters that we want to learn. This first term is the only term that depends on the parameter pi, which is the probability that a class is spam. And so what we're going to do first is just focus on this first term, and we can maximize it independently, because remember, we're maximizing the log likelihood of the data. So to maximize the first term, we'll set pi is equal to the probability that Ci is equal to 1. And so the probability that the ith email is spam can be compactly written as this probability. And remember, this is back from our example of coin flipping. This is nothing more than the probability distribution of treating the probability of spam as a Bernoulli random variable. And so this is the likelihood of the Bernoulli random variable, regardless of its assignment. So if the email is actually spam, then the probability of it being spam is just pi. But if the email is not spam, the probability is 1 minus pi. And we're writing this down compactly. And so the summation of log PCI is just summation of Ci log pi plus 1 minus Ci log 1 minus pi over each of the n examples. And you should recognize this as being basically identical to doing maximum likelihood estimation in the coin flipping example. Because what we're doing here is we're maximizing the likelihood of the parameter associated with whether or not an email is spam, and we're treating that parameter as a Bernoulli random variable. And so the maximum likelihood estimator from what we've derived previously is just the number of spam emails in the data set divided by the total number of samples. So we just use the result that we derived in the first half of the class to figure out what the MLE estimator for pi is. Any questions about this so far? I mean, if you wanted, you could go through the gradient calculations yourself and you'll get the same answer. But the easiest way is to just map it from the problem that we had in the first half of the class. Okay. And now we also need to learn the other 2D features. So to learn P of xj is equal to 1 given C, we're going to maximize each of these summations. And we have D such summations in our log likelihood term. So this is the log likelihood term. We note that the summation over D is a summation over D things that don't depend on each other. So we can maximize each of these terms separately. So we're going to look at one of the terms in this summation, and that's going to be theta jc. And so theta jc is going to represent the probability that feature j is equal to 1 given class label C. And so the probability of the ith email having feature j be 1 is equal to this probability. So this is the parameter for that feature j given class label C, and we're going to raise it to the exponent of whether or not that the ith email has a 1. So in the ith email, we're asking what's the probability of seeing feature j in the ith email given class label C. That's just theta jc raised to xi times 1 minus theta jc raised to 1 minus xi. So if in the ith email you do not observe feature jc, then this is going to be 0, and you'll take 1 minus theta jc as the probability of feature jc in that email. And remember, we're summing the logarithm of this term up over the entire data set. And as I mentioned to you before, you actually care about learning 2 parameters per feature. One when the class label is 1, and the other when the class label is 0. So when the class label is 1, you have the following as the log likelihood. And again, this is just treating the existence of the feature as a Bernoulli random variable under class 1. And this is the log likelihood of that Bernoulli random variable theta j1 for the ith email. Similarly, for the second case, where it's not spam, you'll end up maximizing the log likelihood of theta j0, which is the probability that feature j occurs in a not spam email. And I won't go through the derivation for this, but you can effectively write down the maximum likelihood estimate of theta jc as the fraction of word j occurrences within each class. So when theta hat jc is the summation of the indicator function where xj is equal to 1 and ci is equal to c, divided by the number of times ci is equal to c. So let's substitute that in for the case where c is equal to 1. So in the case of spam emails, what you're going to do is you're going to count the number of spam emails that you have. That'll be your denominator. And within each of the spam emails, you'll count the number of times feature j occurs, and that'll be your numerator. So the maximum likelihood estimator is the fraction of times feature j occurs in a spam email. That's theta j1. For a non-spam, for the second parameter, that's theta j0, which is the probability of feature j occurring in a non-spam email. What this estimator is going to do is that it's going to count over all the non-spam emails. So if you have 40 non-spam emails, your denominator would be 40. And for each of those non-spam emails, it'll count the number of ones where feature j occurs in a non-spam email. So it's a fraction of times the word occurs in a non-spam email. And that's being written down compactly for the 2 cases using this indicator function notation. So I'm going to pause here to see if folks have any questions about what we've done so far in the last 2 slides. Yeah?
Just x. Is x like a matrix kind of? Because like the superscript.
So when it's bolded, it's typically identified as a vector. In this particular case, which x are you talking about?
Just anyone that appears like.
So this.
Superscript and stuff.
Yeah. So this is small xji. So this is saying in your ith. So you have your data set. you're going to pull out the ith data point. So this is xi. So this is xi. And in that ith data point, you're going to look at the jth column. So that's the jth feature in that ith data point. And it's asking, what is the probability of observing that, given that you know the class label is actually ci? Does that answer your question?
Yeah, yeah. Because I was just thinking of X as, yeah, like kind of like a matrix.
Yeah, so the full X is an n by d dimensional matrix. And we're just indexing using j and I, where j is going to index into columns and I is going to index into rows. There's another question. Okay. So this page tells you how to estimate pi, and this page tells you how to estimate JC. And when you put these two together, you get the estimation procedure for all of the 2D plus 1 parameters in the model naive Bayes. So that's how you do parameter estimation in the context of this model. So remember, what did we do in the context of coin flipping? We first estimated the parameter, and then we used that parameter to figure out how likely a coin was to show up heads again. When we have a generative classifier, we do estimation of the parameters of the model, in this case naive Bayes, using the data that we have. And then we're going to use the model in order to do prediction of what the class label is. And as I mentioned before, we do that prediction using Bayes' rule. So we predict the class for new examples by performing what's called inference in the model. And you'll see this term inference crop up both now and in the future. And generally, it refers to the fact that you are estimating or inferring what the class label is given some set of data points. So here you are inferring what C given X is using Bayes' rule. So using Bayes' rule, you get P of C given X times P of X given C divided by, this is just equal to P of X by definition. So this is the result of marginalizing out P of C prime from the joint distribution. And you can write this down by replacing P of X given C in both the numerator and denominator via the naive Bayes assumption here. So you'll notice here, as I mentioned before, that we really only care about the numerator because we can evaluate this for P of C is equal to 1 given X, and we can evaluate this again for P is equal to 0 given X, and notice that the denominator is going to be the same in both cases. And so simply by comparing these two, we can make a decision about which class to predict from this model. And how do we make a decision about this? Well, we're just going to predict the C, the class label C, that has the highest product. So we're going to multiply P of C times the product of P of Xj given C for all the different choices of, for both the choice for C is equal to 0, C is equal to 1, and for C is equal to 0. And we'll predict C as the one that has the higher number. Yes?
Could you only compute one value of C since P of T given X is equal to 1 minus P of not C given X?
P of C given X is equal to not P of not C given X. I believe that should be true. You could check if it's greater than 0.5. But okay, so if you compute the normalization constant, that's true. But if you don't compute the normalization constant, then the numerator alone, it doesn't necessarily have to be a number that's calibrated to be a valid probability. So you can't only compute the 1 and do 1 minus that, because the numerator alone is not set up to be a calibrated probability distribution. So that's why you have to compute both. So let's just think about a really simple example where D is equal to 3. So we have 3 features exactly. What we're going to do in the naive Bayes model is note that to estimate it, we have this pi, we have theta 1, we have 2D plus 1 parameters. So we have pi, we have theta 1, 1, theta 2, 1, theta 3, 1, and theta 1, 2, theta 2, 2, and theta 3, 2. This is the probability of, instead of 1 or 2, you could also do 1 or 0 for like, this could also be a 0 to represent the spam case, represent the not spam case. But the point here is that you represent these 7 numbers, you estimate these 7 numbers from the observed data that you do have. And then when you want to do prediction, you would just multiply all the numbers in the first row and then all the numbers in the second row and look at which one is larger. And you will pick, if the first row is larger, you will pick the class label as 1, and if the second row is larger, you will pick the class label as 0. And in practice, you want to, instead of doing the multiplication of the probabilities, you want to add up the log of the probabilities because that's more numerically stable, but that's the principle by which you will use inference in order to come to a decision about what the class is under the naive Bayes model. Yeah? Oh, yes, you're right. It's 1 minus pi. That's my mistake. Yeah, thank you. Okay, any questions about estimation or inference in a naive Bayes model? Yeah. Yeah, you would just take the log of this equation for c is equal to 1 and the log of that equation for c is equal to 0, and you would compare which one's bigger. All right. And so naive Bayes as an algorithm in a generative model is an amazingly cheap learning algorithm because to estimate the parameters using maximum likelihood, you basically just go through the data from n is equal to 1 to n is equal to capital N, and then you count the number of times a given feature shows up in a spam email or a not spam email. So you can actually estimate all the parameters of this model using one sweep through the training data set. And at test time, you multiply some numbers together and you just compare which one is bigger. So it has a really cheap test time estimation procedure for inference via the application of Bayes rule. And it's important to recognize why it's so cheap. The reason why is because of the model structure and because of the naive Bayes assumption that we made. That's what made our life easier for both learning as well as for inference. And so we did this analysis in part because we started out with a coin flipping example in the context of the Bernoulli random variable, but you can extend this arbitrarily to many, many different other kinds of random variables as well. In practice, this model tends to be much less accurate relative to discriminative models due to the fact that it makes this naive independence assumption. And so what we're going to talk about in the last 20, 25 minutes or so is an extension of this idea that is called Bayesian parameter estimation. So we're going to motivate this. Actually, before we jump into that, any questions about generative models, how they differ from discriminative models, what we did in the last hour and a half, where we, instead of modeling the decision boundary, we use tools from probability theory to model the actual features and model the actual class distributions, and use Bayes' rule to infer what the class label would be for a new test point. So that's the fundamental difference relative to a lot of the discriminative approaches that we've covered in the past before. Any questions about any of this setup? Okay, so in that case, let's talk about one of the limitations of maximum likelihood estimation. So maximum likelihood estimation can often overfit if there's too little data. What does that mean? Let's say you start out by flipping a coin exactly 2 times, and in both instances, you get heads show up. You can write down the formula for what the maximum likelihood estimator for the probability of that coin coming up heads is, and you'll get the number 1. And so the reason for this is simply because a model assigned probability 0 to a tails showing up because it never saw it. And this is this problem of data sparsity, and it represents the way by which these generative models can overfit. They've overfit to the very small subset of observations that you have seen. And so, fortunately, there are ways to get around this. And so in order to get around this, we're going to use what's called a prior distribution. So in the coin flipping example, we modeled the patterns in the coin using this Bernoulli random variable. The Bernoulli random variable had a parameter theta. Theta lies in the unit interval. And what we're going to do right now is define, as domain experts, a prior distribution over what theta should be. And what this prior distribution is going to do is that it's going to encode our beliefs about how we think theta should behave before we observe any data altogether. So if you asked a random person on the street and you asked them the question, I'm going to tell you about a coin that I'm going to flip, and before I tell you anything about whether that coin has landed head or tails, how likely do you think head or tails actually is? Well, they might say, I think it's a 50% chance it's going to show up head or tails. So we want our models to be able to encode the idea that we have prior beliefs about how objects should behave. And in this particular case, the object is this coin that we're going to flip, and the prior distribution is going to be specified over the parameter of the random variable that controls the behavior of the coin, and that's this parameter theta. So we're going to specify this prior distribution theta that's going to encode our beliefs about how coins behave before we see any data. Once we have this prior distribution, then we can flip this coin, and we can observe a data D. And so for that data set D, we'll have a likelihood term. And this likelihood is going to be the likelihood of observing the data set given the parameters of our model. And remember, when we just were doing maximum likelihood in the first thing that we covered in this class, we were just looking at the data and maximizing the likelihood of the data under the model. And that's the exact same term that we have as the second term. But now we have this new term, P of theta, that's going to encode our prior distribution. If we have a prior distribution and we observe samples, we can ask, how do we change our beliefs about what the value of theta is? So in the past, when we didn't have a prior distribution, we just did maximum likelihood estimation on the data to get the MLE estimator. But the problem is the MLE estimator is going to overfit, so we came up with this prior distribution. When we have a prior distribution, we can use Bayes' rule in order to tell us what the posterior distribution of the parameter theta is given the data set D. So given the data set D, the posterior distribution, so this is posterior because it's after we're seeing the data, is equal to P of theta times P of the data set given theta divided by the probability of the data set, which is equal to this integral on the left. So this is just the application of Bayes' rule to the problem of estimating the parameter theta after we've observed the data from the coin flips. So what we're going to do is we're going to take our prior beliefs about how theta behaves and how coins behave in general, and we're going to multiply that by the likelihood of the data set that we actually got. And in this enterprise, in practice, we'll rarely ever compute this denominator explicitly, and in general, what you'll find as you go on into more advanced versions of this class, computing the denominator tends to be intractable. But for now, let's just say we're interested in doing the estimation process for this posterior distribution. What does this actually look like? Well, we already know what the second term looks like, which is the likelihood. And the likelihood of observing NH heads and NT tails under a Bernoulli random variable is given to you by this equation. Because that's just the product over I is equal to 1 to n of xi times 1 minus theta times 1 minus xi. And if you were to actually multiply these numbers together, you can move the product into a summation within the exponent to get theta raised to a summation over I equal to 1 to n of xi times 1 minus theta over a summation of 1 minus xi. And you'll note that the summation over xi is basically a count over the number of heads, because 1 denotes heads. So you get theta raised to nh times 1 minus theta, where the summation over 1 minus xi is a count over the number of tails, raised to nt, which is how you get the equation up top. Any questions about this derivation before it disappears? All right. So this is just the likelihood of our data set. Likelihood of all the coin flips that we observed, given that we have this Bernoulli random variable. And what remains now is to specify the choice of the prior p of theta. So what choice of prior might make sense? Well, if you wanted to have a prior that made no assumptions about whether or not the coin was biased, or whether or not you had any prior beliefs about how coins behave in general, you might use the uninformative prior. And a reasonable choice here is the uniform prior over all the possible values that theta should be. So that's like saying you go to someone random on the street and they're like, I don't know you, I don't trust you, you could have a biased coin, so I have no prior beliefs about what kind of parameter theta should be. So it places a uniform probability distribution that theta can be any number that lies in the unit interval. An alternative, if you go to someone else, they might be, I don't know, I don't think you're working with a biased coin. Most coins end up with a 50% chance of heads. So I'm going to come up with some kind of a distribution over the unit interval that has a peak around 0.5, because that's what I think most coins should have as the probability of landing heads. And so how do we actually encode these beliefs as distributions over the unit interval? And to do that, we're going to use something called the beta distribution. How many of you have seen the beta distribution before? So a few of you, and less than those who know about Bayes' rule. But the beta distribution is a distribution over continuous values in the unit interval. So if you make draws from the beta distribution, you get samples that lie between 0 and 1. So 0.1, 0.11, 0.79, 0.67, these are all valid samples from a beta distribution. And a beta distribution is a distribution that has two parameters, A and B. And the probability density function for a beta distribution is given to us by this equation. And so I've shaded out the stuff here, and that's the normalization constant, which is this ratio of gamma functions. But the term you really need to pay attention to is here. For any value theta that lies in the unit interval, the probability density function for that value theta, given the parameters of this beta distribution A comma B, are going to be theta raised to A minus 1 and 1 minus theta raised to B minus 1. And if we ignore the normalization constant, then we can simply write down that the PDF is proportional to this quantity. The expectation of a beta distribution, and this is just an FAQ on properties of the beta distribution, is just A divided by A plus B. So that's the mean of the beta distribution. But the intuition you should have for how the beta distribution behaves is going to be to ask what happens when you tune the two knobs of the beta distribution. What happens when you manipulate A and when you manipulate B? Well, if A is equal to 1 and B is equal to 1, then the beta distribution actually becomes the uniform distribution over the unit interval. If A is equal to 5 and B is equal to 5, then it follows this red curve. And what's being plotted here is the probability density function of the beta distribution. So it's saying that on average, you believe that most of the probability mass of this distribution is going to lie here. And if A is equal to 200 and B is equal to 100, then it's going to peak at this really, really peak point here. So this is going to be the PDF in the last use case. So by manipulating A and B, what you can do is express different choices of prior beliefs. So if you're someone who says, I don't think any coin, this coin could be biased or it could be completely fair, and I have no prior beliefs about how biased it is. You might end up picking a prior distribution, which is a beta distribution, with A is equal to 1 and B is equal to 1, which represents this PDF. If you're someone who has strong beliefs that the probability of showing up heads is 0.65, you might want to pick this one. The configuration for A is equal to 200, B is equal to 100. So in this way, without seeing any data altogether, just by changing around A and B, what you can do is you can express preferences about what the values of theta should be for this coin. Okay. And now we can see what happens when we try to compute the posterior distribution, which, remember, is the distribution of theta after we have observed the data. So the distribution of theta after we've observed the data is going to be the multiplication of the prior distribution with the likelihood function. And we've ignored the normalization constants here. So this is the probability of the beta distribution without the normalization constant. So this is just the PDF. And this is the probability of observing, n coin flips where you have nh heads and nt tails under a Bernoulli random variable. And what's nice is that you can group the terms together and add up their exponents to get the final form, which is theta raised to a minus 1 plus nh and 1 minus theta raised to b minus 1 plus nt. And what's interesting here is that this looks exactly like a beta distribution with parameters nh plus a and nt plus b. So we can ask, this is a distribution over theta. What is the mean of this distribution? What's the average value of this distribution? Well, we know the formula for the average of a beta distribution. It's a over a plus b. But now this is our new a and this is our new b. So we can calculate the conditional expectation of the posterior distribution of theta given this data set by looking at the mean or the empirical average over the posterior distribution. And that's going to be nh plus a divided by nh plus a plus nt plus b. And the intuition you should have for a and b are as behaving as pseudo-counts, which is because beta of a plus b can be written as beta of 1, 1 plus a minus 1 heads plus b minus 1 tails. So think back to the example that we had where we had exactly 2 heads that we observed in our data set. So nh plus 2 was 2 and nt was also 2. Sorry, nh was 2 and nt was 0. And in the past, when we had the maximum likelihood estimator, which was just this term, we ended up with the theta ml as 1. But now, what these a's are going to do is they're going to smooth out that fraction. Instead of it going straight to 1 because you observe no tails, your priors are going to dictate what the value of this fraction is going to be. And so in the small data setting, what's going to happen is if this is your prior distribution, so here you picked a prior distribution that's peaked at theta is equal to 0.5, this is going to be your likelihood function because the likelihood function is going to be maximized at theta is equal to 1. When you multiply this likelihood with this prior, it has the effect of smoothing out the result. So the posterior distribution is going to take a value that's somewhere in the 0.67 range. But what happens when you have more than enough samples, so let's say you observed 100 coin flips, is that your prior is going to look like this, but both the posterior and the likelihood are going to have the same form. So in this equation here, if nh and nt are much, much bigger than a and b, what that's going to tell you is that whatever your prior is doesn't really matter anymore, because I'm going to use the data to dictate what the posterior distribution of theta should look like. So these prior parameters not only tell you what values of theta you prefer over the others, but it also tells you just how much data you need in order for the model to override your priors. And so the third kind of estimation procedure that you can do is, instead of finding the mean of the posterior distribution, so the mean of the posterior distribution might be somewhere here, you might actually want to find the mode of the posterior distribution, which is you want to find the location that represents the maximizer for the probability density function of the posterior distribution of theta. And that is what's called the maximum a posteriori estimate for the parameter, or the map estimate. So are people comfortable with the idea that the mean of a distribution, or the first moment, need not be the same as the location of the mode of the distribution? And so both of them give us different pieces of information, and it's our preference as to which one we want to pick, and often it's based on our intuition or domain knowledge that we might choose one over the other. But it's important to know how to calculate the mode of the posterior distribution. So to calculate the mode of the posterior distribution, we are going to solve an optimization problem. So we're going to convert the Bayesian parameter estimation problem into a maximization problem. We're going to ask for the argmax of the probability density function of the posterior distribution of theta given the data set. And we're going to use Bayes' rule to point out that this is just the likelihood, this is the prior times the likelihood. And we're going to work with the logarithm of this equation because it's going to preserve the location of the map estimate. It's a monotonic transformation. So you get an argmax of theta over log p of theta plus log p of d given theta. So what do we actually compute that as? So log p of theta plus log p of d given theta becomes nh plus a minus 1 log theta plus nt plus b minus 1 log 1 minus theta. And this is just a function of theta. And we can maximize this function as before by setting this by setting the derivative of this function to 0 and identifying a critical point. So d by d theta of log p of theta comma data is equal to this equation, which is obtained by taking the derivative of the right-hand side. So the derivative of log of theta is 1 over theta here. And the derivative of log of 1 minus theta is minus 1 over 1 minus theta, which is how you get this equation. And by doing the same algebraic manipulations that I showed you how to do a few slides ago, you can prove that the map estimator has this functional form. And this is just, again, an equation in the numbers that are coming from your data and the numbers that are coming from your prior. So we can actually study how these things stack up. So remember, we had two scenarios, the small data scenario and the large data scenario. And so let's focus on the small data scenario first. What motivated this exercise was this observation, which is that when we only had two samples, we might end up overfitting. And because this probability, the maximum likelihood estimator, doesn't see any tails, it assesses that the likelihood of seeing a heads in the future is always 1. And this makes it a bit of a useless model because we know that the reason it's making that prediction is because it hasn't seen enough data. So we can use a prior distribution to smooth out its prediction. And this prior distribution will pull back the expectation of the posterior distribution, will leverage the prior distribution here to pull back the estimate of what theta should look like. And it'll go to about 0.67. And finally, you can actually solve the optimization problem. If you didn't want the mean of that distribution, you can also ask for the mode of it. And that would give you this equation here, where if you plug in these numbers into this equation, you get about 0.75. And these are very different kinds of numbers. And they should tell you that this entire enterprise of Bayesian inference is going to be dependent on a practitioner's ability to reliably write down what the priors are and reliably specify the priors, as well as the amount of data that they have for those priors to get overridden eventually. But as you go to the large data regime, you'll see that all these three numbers start converging to about 0.55, which converge to the maximum likelihood estimator. And that's because all of the prior distributions that were written down initially start becoming overridden when you see more and more samples. And so you should know that the theta map is always going to assign non-zero probabilities as long as a comma b is greater than 1, and that's just by definition of what this equation is actually going to do. Okay, so to summarize, what we talked about today is just a very different way of doing prediction. Like, we didn't want to learn a functional mapping from inputs to outputs. We wanted to learn what made the data from a given class the data itself. Like, what makes a spam email spam? And to answer that question, we use random variables to characterize the probability of events that happened in the input space. Because in discriminative modeling, we've pretty much ignored the input space altogether. We sort of just said, here's the input space, and as long as those features are normalized, you're going to multiply them by some numbers till you get a probability of an output. Versus here, we flipped that paradigm and said we want to model how likely inputs are under different classes and use this Bayesian machinery in order to come to a decision about what the right class to predict actually is. So it's really important you have a strong sense of understanding of what this Bayesian machinery is and are able to distinguish between these three styles of learning and inferring the posterior distributions, maximum likelihood estimation, the expectation of the posterior, as well as the map estimate, and you know when to use which one. Okay, so with that, I'm going to stop. All the best for your midterm. Remember, double-sided age sheet. Just bring a calculator. I don't think you'll need it. But also bring your student cards because we're going to need to take attendance when you show up. Yeah, yeah.